Hi everyone, welcome back to the ML Algorithms Coding series. In this particular session, this is I think the ninth session of our series, and in this particular session, we will learn more about the neural networks algorithm. And in that particularly, we have started neural networks in the last session where we discussed about the perceptron. In this particular session, we will discuss further about the feed-forward neural network. So by this time, I think like for understanding this thing, you already have a basic knowledge of neural networks. However, I'll just go a brief up of about how we are considering a simple neural network. For example, let's consider in the input layers, we have four variables. Then in the hidden layer, we have three variables and then one output variable. So this is like input goes, then we do some calculations, and then based on that, we get the output. So when we go like from the input then to the doing calculation till the hidden layer, then till the output layer, that is what we are going is we are doing the forward propagation. Once we get the output, like generally the weights and biases we do not know at the point of when we are training the neural network for the first time. So then we will readjust the weights and biases of the different neurons while going back, and this process is known as back propagation. We do go forward and backward until we get to some optimal values or until we get to some number of iterations or something to quantize that thing. So that's a very brief. I hope you understood what I wanted to say. In case if you still think there you like a little bit of understanding of neural networks, I suggest you to go and watch some basic videos of how neural network works. Moving forward, like if we see through the forward propagation and backward propagation, we can easily get to the calculations. So calculations we'll get for the first neuron that we have, we can calculate it by the input into the weights 1 plus bytes 1, we get the z1. And for the z1, if we use the railway activation function, we'll get the a1, where a1 is the output of the first neuron. For example, and similarly we do for Z2 where we take A1 plus A1 into weight 2 plus B2, we get Z2 and then we do apply this thing, then we got the final probability. Right, and similarly we do for back propagation. Before I explain further, let me tell about the nomenclature that I use. Here X is the input, W1 is the weight matrix connecting the input layer to the hidden layer of shape. B1 is the bias vector for the hidden layer. E1 is the output of the hidden layer. Similarly, for the neuron 2, W is the weight matrix for in the hidden layer to the output layer of the neuron. So particularly, so what's happening is we might have some neuron here, and then we particularly have one neuron here, then we have the second neuron here, and then the final output here. So this one is called input. This one, for this we'll have weight 1 and bias 1. For this one we'll have weight 2 and bias 2. And finally this will be the output. Okay, and similarly, now for the delta tree, what we are seeing is the final probability that we got. And then dw2, for calculating dw2, will apply the chain rule, in which we will we'll multiply the transpose of a1, the output that we got from the first neuron, multiplied with by the difference of w2. So we'll get dw2, and similarly, if we use delta 3, we'll get d bias of 2 db2. Similarly, if you want delta 2, what we'll have to do, we will have to do again a dot product, where we'll take the delta 3 that we got into the weight 2 transpose, and similarly for dw1 we'll multiply it by the inputs that we have earlier, and then this will sum of delta 2. So I hope you understood what we just did here. We will, in the coding part, we'll just write this thing as code. Particularly, so we are saying this is a two-layer neural network where we are randomly initializing the weights. The weights as random initialization, and the biases as zero initialization. And then here we have written like This is we have defined in the in the forward prop. We have defined like the Z1 is how do we define Z1 is nothing but this thing, Z2 nothing but this term. So Z1, A1, then Z2 exponential, and then finally probabilities. And then for loss, what we are saying is for the loss, what we are trying to do is like we'll first do the forward pass, and then we'll take the logs of those probabilities, and then the data, then we'll try to compute the data loss. And then finally, for I think by data loss here we means for each and every forward prop or whatever we are doing, the loss in data or the loss in output that we are getting. And for that we're using log probabilities. For that we are taking probabilities and taking logs of those probabilities and then summing up those logs of probabilities and then uh, just dividing it by the number of parameter inputs that we had so that we get a loss for each input node that we had. And then in the train, what we'll be doing, I think we'll be doing two things, is forward prop plus backward prop. So in this particularly in forward prop, we are just doing similar to what we did earlier. And then we are doing like a backward prop similar to what the calculations that I explained earlier, W2, W1 from delta. And then finally we update the weights and biases. Once we have done that, so we try to see like if we have if we are on every 100 iteration of the epoch, we just say we just print what's the loss, like how are we doing, and then we are doing number of epochs. We have mentioned how many epochs that we have, and we are running the whole loop for those epochs. So two-layer neural network, input size, hidden size, output size is arguments. Then we calculate the weights and biases. Biases of the two layers initialized by inputs, forward loss functions, loss between the predicted probabilities and true labels, and the train function is based on the calculated gradients. Similarly, for testing this thing, we'll generate a nice random set, we'll train the neural network, and then we'll generate. So I'll say in this particular session, this might goes too big, but I'll try to explain these things in this particular session only. So there are several ways how we can improve the implementation of our two-layer neural network. So first is for weight initialization. The current implementation initializes the weight as using a random Gaussian distribution. However, we can use Xavier or He initialization to improve convergence and avoid vanishing or exploding gradients. And then the learning rate decay. So generally what we are doing is like the learning rate is hyperparameters. However, using the fixed learning rate may lead to suboptimal performance or slow convergence. So that what we did, we can use a common technique such as decreasing the learning rate over time. It's like using as also known as learning rate decay. And I think like that's a very easy intuitive. What we are doing is we are just multiplying every time by 0.95 so that we are decreasing the learning rate every time at every 100 epoch or mm, at every 100 epoch. Third is regularization. So a lot of times it is prone similar to how we have seen in the linear regression. This is and other different machine learning models we have seen like these things are very prone to overfitting, and to overcome overfitting, we can use L1 or L2 regularization. If you don't have a good idea, please go and watch my previous videos where I have may explain the L1 and L2 regularization. And the third thing is like the current implementation updates the ways using the entire training set at each iteration, which can be computationally very expensive for large data sets because if you have million entries at once, it might run out of memory. So an alternative is to use mini batch training, in which a random subset of the training data is used at each iteration to update the weight. This can speed up the training process and improve the convergence. So in this, we have defined the each batch size as 64, and for each epoch, we are running it for one batch. And then finally, the optimization algorithm. The current implementation uses SGD is an optimization of algorithm. However, there are better algorithms such as ADAM, ADAGRAD, or IMS prop, which can improve convergence speed and also the very important thing of performance of the network. So a lot of times what I've seen is generally ADAM optimizer is used. So in this particularly how we updates the weights is somewhat different. So earlier what we were doing is like you're just updating the weights in a very common fashion. So if you see for updating the weights, we are seeing W1 equals to the earlier W1 minus learning rate into DW1. However, here what we are doing is MW1 W1 equals to W1 minus learning rate into beta 1 into MW1, and then we are just 1 minus beta 1 into DW1. So there are a lot of parameters involved. But I think here what particularly is happening, instead of learning rate, we are also taking into consideration of this beta and beta 1 and beta 2 for multiplying each and every time. And other extensions arbitrary in loss, different activations function, different loss functions, and we can have multiple layers. So I think you would have got a better understanding of how to implement a neural network feed forward neural network as in the coding. And I think like if you just went to the video, one of the good advice that I got earlier and I would like to pass it forward is try to see through the video that I just told, go back and try to implement the algorithm on your own. And if you are not able to write those things, like mostly you might get stuck. So if you are not able to write those things, just go back. I'll share the link of this particular repo by Alireza. Just go back and see where you got stuck and try to understand these things and write code on your own. And once you write the code for these things once or twice, you'll be very good at understanding. You'll be better than 90% of the people at understanding of the neural networks. So I wish you all the best, and thank you for watching this lecture, this session of the series. And in case of any comments or feedback, please let me know in comments. Thank you very much.